math, a transform is generally something that turns one function into another function. There's a lot of different transforms. Today we're going to take a look at the Laplace transform, and hopefully a transform has properties that make it useful for certain applications. Of course, it's differential equations, so we're going to see how this is helpful for solving differential equations. But before we can get that far, we have to actually take a look at what the Laplace transform is. Well, by definition, you say that you're going to do the Laplace transform of some function. Now, we use the script EL here, and the whatever you're doing the Laplace transform goes in these curly brackets. Now, by default, we're going to start with functions of t. Now, what the actual definition is, it's the integral from 0 to infinity f of t e to the negative st dt. All right, now notice by doing this, since we're integrating with respect to t, this letter s is a constant with respect to this integration. And since we have bounds, this function's not going to have any t's left in it when we get done, and we're only going to be left with a function of s. So generally we say that this gives us some big f of s. All right, so we're going to take a look at today just actually applying this definition to see if we can find the Laplace transform of some basic functions. So let's start with just a super basic function. What about just the Laplace transform of t? Well, this is the integral from 0 to infinity t e to the negative st dt. Well, a couple of things going on here. First off, we're integrating with respect to t. Again, the s is a constant, and this is an improper integral because we have an infinite bound. Remember, to do that, we need to turn this into a limit. I don't care what letter you use. I'm going to do the limit as b goes to infinity, the integral from 0 to b, t e to the negative st dt. All right, to integrate this, we're going to do by parts. By parts is going to show up a lot here because you see you have two different types of functions multiplied together most of the time. So we picked one function to be u. That's what we're going to take the derivative of. Of course, that's going to be t. And then everything else up there is dv. So du is just dt. And when we integrate this, this is negative 1 over s e to the negative st. So this is the limit as b goes to infinity. Excuse me. All right, so remember by parts, it's uv. So it's negative t over s e to the negative st minus the integral of v du. So minus and minus, so that's going to become plus 1 over s e to the negative st dt. All right, now again, we're integrating with respect to t, so this s is a constant for this piece. So it's up here. So this is the limit as b goes to infinity. We have negative t over s e to the negative st plus, let's go ahead and just pull that s out, e to the negative st dt. So the limit as b goes to infinity of negative t over s e to the negative st. And of course, when we integrate that, that's negative 1 over s e to the st. Now I'm going to go ahead and put my bounds back on here because that's what we have here, the top endpoint minus the bottom endpoint. All right, now since we integrated with respect to t, that's where the b is going in. So this is the limit as b goes to infinity. This is negative b over s e to the negative sb minus 1 over s e to the negative sb. Minus, so when we put 0 in for the t, this one's going to be 0 minus, that's going to be 1 over s. Okay, so top endpoint minus bottom endpoint. Now let's go ahead and evaluate this limit. Remember, since this has a negative exponent, let's write this as one more step as b goes to infinity. This is really b over s e to the sb minus 1 over s e to the sb and plus 1 over s. Now I assumed here, in this case, we know b is positive because it's going to infinity. Now I'm assuming s is positive to bring it down here on the bottom, so this is only true if s is greater than 0. If not, s would be negative, and that would actually be on the top. So as long as s is greater than 0, that would go to the bottom. Now as b goes to infinity, this here would be infinity over infinity. You could do L'Hopital's rule, or just notice that linear term is going to be completely outrun by this exponential term. So this piece right here, if you don't believe me, do L'Hopital's rule, is going to go to 0. Here you have a constant over an exponential, so that is also going to go to 0. So all we end up with here is 1 over s. So the Laplace transform of t is 1 over s. All right, so there you go. This is a basic idea of how to do a Laplace transform. We're going to do one or two more just so we can kind of see. Let's start back over here and maybe do, what if we just had some type of exponential? What if we had the Laplace transform of e to the something t? All right, by definition, that's 0 to infinity, e to the something t, e to the negative st dt. Well, since here we're multiplying, we have like bases, we can actually, let's go ahead and turn this to a limit also. We can actually combine those two right there. So it's the limit as b goes to infinity, 0 to b, e to the like bases, we're going to add those exponents, so that's at minus st dt. Or we can rewrite that as 0 to b. I'm going to write it like this. This is negative s minus at dt. Now I brought the negative out front, so it kind of kept this same format here. Now remember, s's and a's are constants in this case. So if these are constants, this is just like e to the negative 5t or something like that. So that one we can actually integrate directly. So that would be from 0, let's go ahead and integrate it. Negative 1 over s minus a, e to the negative s minus a t, evaluated from 0 to b. Again, top endpoint minus our bottom endpoint. So it's the limit as b goes to infinity, negative 1 over s minus a, e to the negative s minus a b, minus negative 1 over s minus a, e to the, well, 0. So limit as b goes to infinity. Now, it's kind of the same thing that we did before. This exponential, I can rewrite that on the bottom as long as that exponent stays negative. So I want to write this as this, e to the negative s minus ab. Of course, this is just plus 1 over s minus a. Now, the reason I want to do that is because that'll make this thing go to 0 as b goes to infinity. But the only way that's true is if s minus a is greater than 0, or if s is greater than a. So that's the caveat that we have to do here. Now, as b goes to infinity, this here is going to go to 0. So this would just give us 1 over s minus a. So the Laplace transform of e to some power to t, like e to the 5t, e to the whatever, is 1 over s minus a. Okay, so notice for our last two examples, we put in a function of t and got out a function of s. All right, let's try one more basic example here, maybe a little bit harder to do with the integration. Give me a little bit more room here. So let's say if I say, what's the Laplace transform of let's just do just sine t. Well, by definition, that's the integral from 0 to infinity, sine t times e to the negative st dt. Now, this is a much harder integral to do. You still have to do this by parts, but we don't have a function that's going to go away. So this is what we call a wraparound integral. So what I'm actually going to do is I'm going to just focus on this real quick, and then we'll go back and put the limits and everything else on there. So how do we actually do this integral? Well, like always, we pick one function to be u, everything else is dv. Pick whichever one you want. I'm going to let the exponential be u, everything else is dv. So the derivative there is going to be, remember, taking the derivative with respect to t, so it's negative s e to the negative st. And when we integrate sine, well, it's going to be cosine t. Is it positive or negative? We'll check. The derivative of cosine is negative sine, so we know we need the negative there. All right, so this integral is going to be equal to uv, so negative e to the negative st cosine t minus the integral of v du. So we got a minus, 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 so overall negative. S is a constant, e to the negative st cosine t dt. All right, we got to do by parts again. Since we let u be the exponential before, we want u to be the exponential again, so e to the negative st. dv will be cosine t dt. So du is negative se to the negative st, and dv is the sine of t. Quick check, the derivative of sine is cosine, so that works. All right, so this is negative e to the negative st cosine t minus s times, because that's out front, and what's this going to be? uv e to the negative st, that's a mistake. uv e to the negative st sine t minus the integral of v du. Now we have another negative, so that's plus s e to the negative st sine t dt. All right, so let's see here. So let's go ahead and distribute that. So this is equal to negative e to the negative st cosine t minus s e to the negative st sine t minus s squared integral e to the negative st sine t dt. All right, now notice on the far end here, we ended up with the exact integral that we started with. And remember, that's actually what's on this side of the equation, negative st sine t dt. So what we're going to do is move everything to one side, because that's what we're trying to find. So this will be the integral of e to the negative st sine t dt plus s squared integral e to the negative st sine t dt is equal to, well, the other side, negative st cosine t minus s e to the negative st sine t. Here we can factor out this integral, so I get s squared plus 1 times the integral of e to the negative st sine t dt. And of course the same thing's on the other side. Cosine t minus s e to the negative st sine t. All right, so we finally have our answer. The integral of e to the negative st sine t dt is equal to, well, just divide this side by s squared over 1. So I'm going to write this as negative 1 over s squared plus 1 e to the negative st cosine t minus s over s squared plus 1 e to the negative st sine t. All right, so there we go. That would be just the integral of basic function. But remember, we're trying to do our Laplace transform, so now we need to put back on our bounds. So if we do kind of the same thing, let me go ahead and make some room here. We could go ahead and make this our limit as b goes to infinity from 0 to b, which means on this side, since we've already integrated it, we want to go from 0 to b, and we got our limit right here. Okay, so this will be equal to the limit as b goes to infinity. Top endpoint, let's put the b in there, negative 1 over s squared plus 1 e to the negative sb cosine b minus s over s squared plus 1 e to the negative sb sine b minus. All right, when we put 0 into here, e to the 0 is 1, cosine of 0 is 1, so that's just negative 1 over s squared plus 1, minus, the sine of 0 is 0, so that goes away. So let's look at all of this. Limit as b goes to infinity. Now again, I want this exponential to make this go away. If not, it's going to run off to infinity, and that's not going to be very helpful for us. So I want to write this as s squared plus 1 over e to the sb cosine b. Because if it's on the bottom, then this can make this whole expression go to 0. Well, to go to the bottom, s here would have to be positive. So this is only going to be true, I'll write it way over here, if s is greater than 0. I want to do the same thing for this piece. That'll be s over s squared plus 1 over e to the sb sine b, and then plus 1 over s squared plus 1. All right, so cosine as b goes to infinity is just going to alternate between 1 and negative 1. Since the exponential is going to infinity, 1 over infinity, means this whole thing over here is heading towards 0. Same exact idea here. Sine's going to alternate between 1 and negative 1. This is going to 0, so that drives all that to 0. So the only thing we have left is 1 over s squared plus 1. So the Laplace transform of the sine of t is 1 over s squared plus 1. Now to save us just a little bit of work here, you can kind of see a little bit of what would happen if we had done cosine instead. Well, you're going to have some sign changes along the way, but the idea here is these sines and cosines here would be switched because we started with the opposite one. Which means when we plugged in the 0, this one would survive and this one wouldn't. So we can kind of see from this that the Laplace transform of the cosine of t would have given us this piece, which would be s over s squared plus 1. All right, do me a favor, make sure that you go through and actually try that one to see that you can get it. Now, we're going to see in this section that we actually have a Laplace transform table that has a lot of these basic rules for us. Kind of like when we first learned how to do the derivative using the limit definition, we generally don't do the Laplace transform using this long method. Generally, we just go straight to a table to get to our answer. But it is important that we remember how to do all these basic skills. But for a large part of it, you're going to use a table to come up with these.